जी अस्सलाम वालेकुम। मुझे पता है जी 2 बज गए हैं, जरा हमें थोड़ा सा टेक्निकल हिच है। वी आर अनएबल टू गो लाइव ऑन फेसबुक। जस्ट गिव अस अ मिनट और सो। आई जस्ट फिक्स दिस प्रॉब्लम एंड देन कम बैक टू यू। आई थिंक इट विल बी रिजॉल्व वेरी सून। Yes, the problem has been resolved. We are now live on Facebook also. And do I see the speaker? I don't see the speaker at the moment, Rehan Wainsa. He is there, but he's not on the cam. Anyhow,
Yes, Tarsal, I'm here. I'm here.
you are there, okay. Your video is, I think your cam is
Yeah.
not on.
Yes, let me turn it on.
It is the 4 minutes past 2. I'll just wait another 2-3 minutes to give chance to more and more participants to join. And we have sufficient participation at the moment, but few people, I'm just waiting. और लोग आ रहे हैं जी, ज्वाइन कर रहे हैं। मैं जरा इनको एक दफा एंटर कर लूं रूम में, देन आई विल स्टार्ट। इस तरह से अटेंशन डाइवर्ट हो जाती है, बार बार मुझे एंटर करना पड़ता है। जस्ट वेटिंग के लोग सारे पूरे हो जाएं। तुम एंटर कर सकते हो ऐसे, तुम तो कहते हो कि मैं नहीं कर रहा हूँ आपका।
आप करें, अगर आप कहते हैं तो मैं एंट्री करती समझ।
कहाँ से करोगे?
वहाँ आके आपके पीछे बड़ी होती जो होगा ना, वहाँ आके एंटर कर देंगे।
चलेंगे, 3-4 लोग और आ गए, मैं जरा इनको भी enter करता हूँ। आ गया। रियाज आपने ज्वाइन कर लिया?
यस, अपने अलाउ कर लिया, वो नाम नहीं मेरा डेल आ रहा है।
मैं चेंज कर दूंगा उसको बाद में, डोंट वरी, मैं कर सकता हूँ। Bismillah ar-Rahman ar-Rahim. In the name of Allah, the most gracious and the most merciful. Ladies and gentlemen, Assalamu alaikum. Good morning and good afternoon from Pakistan Society of Civil Engineers based in Lahore, Pakistan. A very warm welcome to all the participants who have joined us live on Facebook. This is technical lecture number 61 of Pakistan Society of Civil Engineers, which for the information of new participants, that we hold one lecture every month for the benefit of young and experienced engineers so that they can remain updated with the new technology and knowledge. By attending this lecture, one can also earn half CPT point, which is recognized by Pakistan Engineering Council. Now, before I introduce the speaker to you and the topic, it's my duty as per rules of Pakistan Engineering Council, I have to read out the rules of this webinar. The first one is all the registered participants must appear live on webcam. However, for the ladies, there is an exception. If they want, they can cover their face, but in any case, they will have to cover they will have to appear live on the webcam. During the lecture, microphone of all the participants shall remain in mute position except that of the speaker. There will be a question answer. This lecture would be approximately 1.5 hours. And after that, there will be 20 minutes question answer session. And this question answer session is only by typing the questions in the text box. You will type the questions in the text box. You can type the questions during the lecture also, and we will note all those lectures. And inshallah, at the end of the lecture, one by one, I will read every question and the speaker would answer those questions. So as far as rules were concerned, these are the rules which I have just spelled out. Now about the lecture and the speaker. Today's topic is existing buildings analysis and retrofit. And before I introduce the speaker to you, I have one apology to make. I'm to Mr. Rehan Wine. His name was mistyped by oversight, and it was misspelled, which altogether changed his second name, and we are very sorry for that. That was a mistake on our part. Now, the topic, as I said, is existing buildings analysis and retrofit. And today's speaker is Rehan Wine, and it is W-A-I-N Wine, not W-I-N-E, as we made the mistake in our advertisement. He is master's in structural engineering, the degree he got from University of California, San Diego, USA. In his 10 years old professional career, he has accomplished deliverance of about $2 billion worth of diverse projects in concrete and steel construction in the Los Angeles County and in Pakistan. Projects range from Los Angeles International Airport, financial district plazas, schools, and existing building, seismic valuations, and retrofits. He was a member of structural design team that upgraded Los Angeles Airport for the 2028 Olympics. His experience of working in United States also include working closely with Building Department of Los Angeles and Los Angeles Airport authorities. Currently, he is the Chief Executive Officer of XForm, a consulting firm based in Lahore. So this was a very brief introduction of Mr. Wine. So Mr. Wine, the floor is yours. Please start your lecture now. Thank you.
Thank you, Tarsal, for the kind introduction. I'll go ahead with the screen share. And before I start the presentation, I would like to welcome all the participants, my seniors and colleagues and everyone to the today's talk. I hope it's a beneficial talk for all of us. So the today's topic is existing building analysis and retrofit. And as Tahir Sahib has already given my introduction, so I will skip my intro for now and I will just jump into the content. So the outline of the talk today is that we want to first talk about the importance of the existing infrastructure and understand like how important the existing infrastructure is for an economy of a country and how we can reuse it and bring it to the best of the use for long purposes. The secondary area where we're going to touch on this presentation are the typical failure patterns that we have seen in especially in Pakistan or the developing countries, and we look into some case studies as well. So in the third section, we will talk about the types of work and evaluations in existing buildings. So we're going to try to understand that existing buildings are not handled in the same way as new buildings, right? So the nature of the work is different and the evaluation processes are also different. So we will touch base on these processes. I do not have the time to go into the detail of each analysis types and evaluations, but we will touch base on all the key aspects. And the fourth area is going to be, we'll talk about the existing, international existing building code, and we'll see how it's different from the IBC that we're used to typically using for our new building codes, how it compares to that. And then we will talk about ASC 41, which gives you basically the loads that you use for the existing building. So it's an equivalent of ASC 7. So like we use ASC 7 for the new code, we use ASC 41 for the existing building analysis and retrofit. And towards the end of the discussion, we'll see some of the retrofit examples, some typical details. Those are not like applicable to all kind of retrofit works, but it kind of shows you the intent of how the strengthening of columns, beam, and slab we can do. So this is a broad overview and a summary of how we were going to start. So let's start from the importance of existing infrastructure and try to understand like what's the importance of the infrastructure. So infrastructure has a very close relation to the economy of any country. And typically Asian countries have been spending close to 5% of their GDP to the development of the infrastructure, with exception of China, of course, which has been spending approximately 15 to 20% of their GDP towards the infrastructure development. But typically it's been ranging in the range of 4 to 5% in our region. But unfortunately, in case of Pakistan, we have spent approximately 1.5 to 2.5% of our spending has been directed towards the infrastructure. So what a good infrastructure will do is that it's pretty important for your economic and social development, of course, and it provides the connectivity between the different parts of the country, either through transports or communication. And it also helps in attracting the foreign direct investment. So the infrastructure is pretty vital for the economy of a country. The second topic that I want to talk about is the land development. So where existing buildings, where it's very important that we understand the importance of the existing buildings is in terms of land development. Because as we can see, especially our urban centers like Lahore and Karachi, they have expanded a lot, especially in the last 20 years. And now we're starting to eat our green fields and the areas which were agricultural lands just a few years ago. In order to curtail the horizontal expansion of the cities, it's important that we have a good sense of how to reuse our existing buildings. And we can, if there's some deficiencies, we can bring it up and we can use it for a longer period of time instead of horizontally expanding our cities. So the third area that's really important to consider is how to build resilience. And by building resilience, I mean we need to have an understanding of the future disasters or any kind of unforeseen circumstances that can cause a damage to the existing infrastructure, which would hamper the economy and also the downtime that's required to bring the infrastructure back to its original state. And the fourth sector that's really important is I would say again it drives the economy is the tourism industry. So the tourism industry has a very close link to the existing not just the infrastructure projects in terms of like roads and bridges, but also how we are able to maintain the character of our historic buildings. So I would just like to give an example of two areas, especially like if we see the Western Europe, 10% of the GDP of the Western Europe is coming out of the tourism industry. And the reason they have been able to do this is because they've been able to maintain the character of the building, the outside facade. But if you go on the inside, they have pretty much renovated the buildings and done all the retrofits required so that they can keep using those buildings. But you will find buildings that are dating back to 1300s, 1200s, even some of them are like before the birth of Christ. We have a lot of buildings that are historic buildings, especially in Lahore, Multan, Bahawalpur, even in the north towards Hunza and Kashmir. So to get the maximum benefit out of the tourism, it's important that we are able to maintain the character of our historic buildings. So the image that you see right now on your screen is a 3D image that was developed using the GIS system. It's the city of Lahore we live in. And you can see, if you can see my cursor, there's like this is the Ravi Bridge. And on the left side, on the top left corner, you see the Shadra town, right? And on the right side is the old city part. And you see the Greater Iqbal Park. And here towards, you would see if I can annotate on the screen. I hope my annotations are showing up. So this is the walled city of Lahore, right? And this I'm circling right now is the Ravi Bridge. What you can see is that we are living in a very densely populated, our urban cities are pretty densely populated, and they have all sort of constructions. Some of them are code compliant, some are not code compliant. They are the brick masonry, there's brick infill masonry structure, and there are some few minor cases of steel construction as well. But we have a lot of buildings on our hand, and the best way to preserve our greenland is that we can repurpose and reuse and make sure that we can keep using the area that has already expanded instead of going more into this greenfield. As you can see, the greenfield has been is decreasing every time. And this is actually the top part of the city, but if you see what has happened on the southern side, it's even much worse than this. So I'll go to the next slide, which talks about, I want to show. So this was an example from the main city, from Lahore. Now this is what you see on your screen on the bottom left is the picture from a city of Muzaffarabad. And the rest of the pictures that you see, 3 pictures are from the failures that happened after the 2005 earthquake, and they are close to Abbottabad and Muzaffarabad region, these structures. As you can see on the picture on the bottom left, that we have a different kind of construction, and a lot of this kind of construction that unfortunately happened on the northern areas is not code compliant or has not been developed with a good understanding of the seismic hazards. So what has happened is that you would see like a box kind of a structures on the top stories with skinny columns on the stories below. For example, this one, I don't know if it's clear or not, but you can identify a lot of them where they have retails and shops on the bottom story with skinny columns as like maybe 9 inches, 12 inches, 18 inches columns supporting several stories above. And so this is another problem that we have. We are dealing against. The picture on the top left is actually one of the failure patterns from a concrete frame structure, the stuff I'm right now circling. And you can see this is a beam column joint that has opened up. And if you can see, there's pretty much no confinement. It's barely nothing, right? And you can see the vertical rebar of the column has buckled. and it's buckled because there's not enough rebar at the joint. We'll talk pretty detail on the non-ductile concrete frames and the failure patterns, but the same things are happening on the bottom right, the area where I'm circling right now. Same kind of issues we have here. So what you see on the top right is frame structure picture that this structure is in Ahmedabad. And once the 2005 earthquake hit this building, there was a permanent deformation and due to the lateral sway, and there were some hinges formed at the base of the column where I'm circling right now. And this kind of failure were pretty common kind of failures after the 2005 earthquake. So we have several problems at hand, and we'll go over each one of these cases in detail one by one. So another incident I want to share is from the Muzang Hospital Lahore incident. It's the incident of this year actually. I think it happened around the monsoon rain, and what happened here was they had a waiting area that you can see a shed here. People are sitting here for the waiting. And so unfortunate that there was like such a tall unbraced brick wall right above the waiting area. And if you can see, I'm highlighting this height. I'm not sure how tall it was, but it seems pretty high. So what happened is that this wall fell in the out of plane action, and it fell over the people, and per the news reports there were like 12 people who were injured because of this. So it's not like we always have these global failures of big structures. Sometimes something very small could be happening somewhere, and it could have very huge implications for that. So and this kind of scenario happens when there's not a good understanding of the behavior of unreinforced brick masonry, especially for the out-of-plane failure. So I'd like to show you the next slide. If I can run this video.
Rehan,
Yes.
please excuse me for a second.
Yes, sure.
I would like to welcome our new participant, Mr. Jovin Manyori. He's from Tanzania, East Africa. He has joined us for the first time. Thank you very much. And we have been joined by Mr. Zhang Jianling. He's a Chinese national. Thank you very much. Both are civil engineers. So thank you for your time and coming to this lecture. Thank you very much. Rehan, you can continue.
Thank you. So I'll go back to the incident we were talking about from the Muzang Hospital, where there was an out-of-plane failure of the brick wall over the waiting area. So I'll try to play this video from the YouTube, and you'll see what actually happened. So I'll just pause here right now. So you see people sitting here, you see this brick wall, and you'll see what happens. Let's see. So as what you just saw is a very basic thing, right? It's unfortunate. It's not a very mega structure. It's not a 3 or 4 or 10-story buildings that needed to be analyzed. These kind of failures could happen anywhere, and the basic problem behind this kind of thing is that we sometimes do not have a very refined understanding of how the different members behave for different kind of loads. So this was an incident that I wanted to show for the out-of-plane failure of brick walls. And if we go on the next slide, so the next slide shows you basically the two cases, two common failure cases we had after the 2005 earthquake. There were some failures because of the non-ductile concrete frames, and the second type, which is the B I have here, is the unreinforced stone masonry buildings. So both had a different reason to fail. There were some different mechanisms. We'll talk about that in pretty detail, but there were 70 to 75,000 deaths because of the 2005 earthquake. Around 4 million people were displaced, and the loss was 2.6% of the GDP. And these numbers I took it from the World Bank reports. So this is what I was talking before, is that the resilience of our existing infrastructure is closely related to our GDP and our economic growth. So we'll go into the details, but what happened with non-ductile concrete frames is that have a very brittle kind of a failure because the energy dissipation is not distributed over the entire building. It instead happens in a very localized region and typically around the column, in the column or at the joints in the first story where we have low stiffness issues. And the second case, we had the unreinforced stone masonry buildings. The problem with stone masonry is that it has a very low strength for the out of plane action. The strength is for the in plane, but for the out of plane, it's not. It does not have the strength. And it's even in case of stones, it's even worse than the brick. That's another thing because we have giant block of stones and they have little mortar in them. It's even worse than the brick. Another problem is that they are not connected to the diaphragm above. As you can see, they have typically don't have any attachment to the roof deck. So there's no restraint at the top. So going on to the next slide shows you the images of what happens in non-ductile concrete frames. So we know that the philosophy of earthquake, the design of lateral force resisting systems is that for the earthquake that we want our joints and our columns to be ductile enough. We want the hinges to form inside the beam and not in the column or the joints. We never want the joints to open up. We never want the joints to fail or the columns to behave as gravity columns. Like we don't want them to just like sway, right? So the hinge should form in the beams. But what happens in non-ductile concrete frame structures is that the hinge unfortunately forms at the joints. And if you can see the image on the right, you see there is no confinement. So I'm trying to draw the confinement which should have been here. The column stirrups or the hoops should have continued. But since it's at times labor intensive, they tend to skip the stirrups for this reason or any other reason. Poor understanding of the engineering, they don't have the stirrups inside the joints. So you can provide as many stirrups in the beams like this. You can do as many stirrups in the columns. But if you're missing the hoops or you're missing the confinement in the joints, it can never function as a special frame. It can never even function as an intermediate moment. It will just the joint will just open up basically, and all your ductility that you wanted to happen in your beams, or you wanted the columns to behave in a certain manner, would never happen because the joints just busted out. The picture below that you see is a picture from the testing. I think it was taken from UC Berkeley testing. They tested the joints of the non-ductile concrete frames, and what they understood is the conclusions were that it's not just the confinement itself, but also the quality of the concrete. So we know that when concrete is highly confined, the compressive strength increases. The compressive strength of a confined concrete is much more than an unconfined concrete. So what the intent of the code is actually, it's not just providing the hoops for the function of the shear itself, but it's also to confine the concrete core so it does not burst open, right? So these are like the failures that happen in non-ductile concrete frames, and I want to show this stuff. So let's now see more cases of non-ductile concrete frame. The picture that you see on the left is taken from Japan, from the Kobe, after the Kobe earthquake. And what happened here is, like, if you see the structure above, it's pretty intact, right? So you see it seems to be in the good shape. But see what happens see what happened in the ground floor. The ground floor columns just collapsed. And this is just a very classic case of a soft story mechanism. And what happens in soft story is that we have the ground floor, which is open because of the retails or parking, but we have these apartment buildings on the top where there's not just the concrete frame, but there's an infill brick or something stiff enough, which is bracing the frames. So because you are now introducing a weak region in the ground area, right? So your entire energy dissipation is happening here at the ground. But that's not what you wanted in your analysis. So unfortunately, the entire energy dissipation is taking at the ground floor. So this is one of the case of another failure of non-ductile concrete frames. The second that you see on the right is what happened here is it's not the ground floor columns that have failed, but the story above here. So there was some kind of, there could be, I mean, I'm not exactly sure, but there could be either this story was soft compared to the stories above, or it had some torsion irregularity, or there was some strength reduction at this level. So that's why in the codes they have this implication that you cannot have a sudden drop of a strength or a stiffness in adjacent stories, because it wants the structure to behave as one, and it does not want that the entire or a majority of the energy dissipation happens in only certain stories. So these were more examples of non-ductile concrete frame. Now we'll go on the next slide, which basically explains you the formation of plastic hinges on concrete frames. So we know that the basic function of concrete movement frame is to provide stiffness through this. Its function is to provide the rigidity based upon the stiffness at its beam column joint, right? So if I draw a beam, so sorry for the rough sketch, but if this is your beam and this is your column, your majority of your stiffness needs to come from your joint. Your joint needs to be really stiff, right? But what happens if you see in case of hinge formation in the first case, what's happening is you have your hinge that's forming either at the joint or it forms inside the column here, but it does not form in the beam. So if I highlight this as blue, your beam, the hinge should have formed here in this region, inside the beam. But what's happening here now, you have your hinges that are occurring on your column. So once the hinges are inside the column, the stiffness of the story, there's a very rapid degradation of the story stiffness. And now you have a high second order effect as well. So what a high second order effect means is that you have your story shear like this, right? Your gravity loads were here like this. Now you have this huge displacement from your equilibrium position. You have this delta now introduced here. And because you had a hinge form at the column, now your entire structure is swaying too much. It's swaying more than what you anticipated in your analysis. Now you have a gravity load, which is already here because of the dead load primarily in case of concrete structures. Now you have this delta introduced because of the soft story. You have this P and your delta. So you have a new moment here, which is basically gonna kill these columns even further. So that's one of the reasons why you see a soft story collapse. It's the basic theory behind is these kind of hinges that happen. The second image that you see is again a similar thing, but it's happening in a story above where the hinges are forming inside your column. Right, it's another case of not something we want as structural designers. The last case is where you see the hinges are inside the beams. And this is an idealized condition. It never happens that we are able to have hinges over the entire building height, but still we should be able to have the hinge inside the beam. The hinge should never be in the column. Like it should never be in the column and it should never be in the joint, always inside the beam. And if we have a good spread of the hinges forming over the entire height, that means our design is pretty good, that we're able to dissipate the energy over the entire height. It's not concentrated over a few stories. So now I'd like to jump to the next slide. So we talked about non-ductile concrete frames and plastic hinges in pretty detail. Now let's talk about what happens in case of brick or stone masonry, right? So again, this kind of construction is something that you would not find typically, you would not find in IBC or American codes. And the reason for this is that the developed part of the world has transitioned away from the use of bricks or stones as partition walls or as bearing structures. Typically, they have transitioned away from the use in the new buildings, especially. But so a lot of the literature that I found on how to resolve this is either coming from inside Pakistan or from our neighbors, India. So the problem with stone or brick masonries is different, right? We don't have the same problems in non-ductile concrete frame. It's a different animal. We have a different issue. So for example, there was a wall here before, right? What happened is, for example, there was an out of plane, the seismic motion was into or out of the paper, right? So what happened is the stone here just fell off. It's because the wall does not has the minimum capacity for out of plane action. And most of its shear strength is inside the plane, in the direction of the plane. Another issue is that we have these tall walls not braced along the height, right? And in fact, they're not even restrained at the top by a positive connection. Typically, you will not see anything. You will see just a light gauge metal sheet, which is just placed on the top with some wooden purlins or something like that. But there hasn't been any good connection to brace the wall at the top. So the solution they came up with after the 2005 earthquake was what you see on the right side, basically. They introduced these concrete members, which the intent is to break the aspect ratio, right? You now, instead of this tall wall, you have this wall panel that's broken, number one. Number two, it's confined on all the four edges by some concrete members as columns and beams. But it's important to understand that this is not a concrete movement frame. Like if you're looking at this concrete frame, it's not intended to behave as a concrete frame. It cannot. Its intention is to confine the brick and ensure that it has enhanced capacity for the out-of-plane failure. And an ASC 41 actually also has a ratio for the aspect ratio, which I'm showing here on the right. They have an aspect ratio, like you cannot have this kind of wall, for example, a tall wall with small width. And this wall is going to be the favorite for an earthquake to just topple off, right? So they want to limit your aspect ratio, and the way you limit it by introduction of these sill beams or bond beams, basically, with columns around them for confinement. So this is the solution for brick or stone masonry in regions where there's a high hazard of out-of-plane failures. Another very interesting thing that I've actually found from the EERI paper is the Dhaji Diwari, if I'm pronouncing it right, I hope I'm doing, it's a very, I would say, a genius solution that has been developed in the Kashmir Valley. You will not find this in the codes, but the way how they were able to resolve the outer plane failures in Kashmir, in some of the regions where they have these wood laced structures. If you can see, what they're doing is that they have introducing these wooden members to break the aspect ratio, and they are breaking the entire wall into small panels. So this also increases, it's doing the same function. It's confining the stones against out-of-plane failures. And what the EERI paper is, like, a paper came out on December 2005, which was the first one from them after the Kashmir earthquake. And it reported that there were minimum casualties associated with this kind of structure. Although it wasn't like explicitly designed, but it's surprising how well it has performed just based upon the solution that the people of that region had learned over the period of time. And I've seen a lot of testing for this structure. I just Googled and I found that a lot of this structure has also been was tested later on in IITs and also in UET Peshawar by, I think, Dr. Kassar Ali. And what they have found is that this structure has indeed shown much better performance in the labs as well, especially if you nail the wood together. Instead of just placing it, if you are able to connect the wood together with nails, it tends to behave in a much better way. So the next problem that you will see a lot in case of structures that have performed poorly in earthquakes is a poor understanding of the diaphragm action. So what we will typically, unfortunately, do is, like, those structures would have, for example, say we have a shear wall, right? And this was designed for some code level forces, for example, but there was no positive connection with the diaphragm. The connection was not strong enough. And what happened is, like, this connection failed pretty early. And now the forces from the diaphragm were not able to transfer to the walls as intended. What you see on the picture on the right is taken from the ACI 31819, which shows that if this is your vertical lateral force resisting system, right? Your shear wall, it could be a beam of the moment frame as well. So you need to have the dowels that connect the diaphragm, or we say it slab in the bending action. It needs to connect, the dowels need to connect from those diaphragm into the wall, so that that shear that's generated because of the seismic action is able to transfer into the wall. And these collector reinforcement are typically there. The name implies is to enable that the diaphragm is able to collect the force, and the dowels are able to deliver the force to the vertical elements. This is a pretty detailed topic. I don't actually have the liberty to go into depth, but this is the basic understanding of it. So now we already talked about the problems, and we talked about the importance of existing infrastructure, and we saw some case studies. Now let's start on the evaluation or retrofit types in existing buildings, right? So in ASC 4117, I took these three definitions from there, and the way they could be different needs for evaluating an existing building. The first need is a mandatory, right? What mandatory means is that, for example, there are some structures with some significant structural deficiencies, and the building department in that, with some authority in that jurisdiction, passes an ordinance that so and so buildings have been flagged because they have, for example, a soft story, they have some issues and they need to be rectified. So in that case, it's a mandatory evaluation that you are required, the owner is required to do that evaluation or retrofit. Because the city has passed an ordinance and they need to comply with it. So this is like the first type that you will see in case of evaluations. The second is the voluntary. So what voluntary seismic evaluation or retrofit means is that the owner himself wants to bring up the performance of their structure, because, for example, they talk to the structural designers in the field and they say that, okay, some earthquake might happen in the future, and they want to bring up the performance to make sure that their building can behave well when the hazard sets in. So in that case, we classify it as a voluntary seismic evaluation. And the clauses are different for each case. That's why I'm mentioning it here, because it's not the same in terms of code. You're not supposed to deal it in the same way. They are handled in a different way. And the last type is the triggered. So what triggered means is basically, for example, you have an existing building, right? You did some kind of a change, or you made something, you increase the forces, for example, like you increase the loads on your existing building, or you cut some openings into your existing lateral members, or you made something worse in terms of forces or decreased capacities or strength. Now you're basically triggering the requirement that you need to check your building for certain conditions. It might trigger a full building analysis, or it might trigger a certain localized area. It depends upon the code, but it basically depends what you are doing to the building, how much you're altering the existing building. So these are basically the three requirements that trigger an evaluation of existing building. So moving on to the next slide. So the next slide talks about the types of works that you will see in case of new buildings, right? So we talked about in the previous slide, we talked about the reason for evaluation, and on the next slide here, we will talk about some of the types of the works that we need to do typically on existing buildings. We'll see that the first type is of repairs, right? What repair basically means, as the name implies, is like something, for example, you had a problem with a beam or a column that you need to just maintain or correct the damage. You want to bring it back to its original character, or you can increase the performance as well. So in that case, it's handled as a repair work. The second is alteration. What alteration means is, alteration is not a repair. It's much more than a repair. But inside alteration, it's a very broad definition. That's why the code has classifies alterations as level 1, 2, and 3. And what alteration level 1, 2, 3 means is basically how much you're altering. So if it's just the architectural coverings and claddings are coming off and you're just changing the, for example, let's say the ceilings or the doors and windows, it could be level 1, and it could be level 2 if you're doing a significant of architectural rework over an extended area. And it could be an alteration 3 if you are basically working over an area which is more than 50% of your entire building. And the reason for defining these works separately is because, again, the code handles all these types of works differently. It's not handled in the same way in terms of the code perspective. The third type is the change of occupancy. So the change of occupancy means is, for example, you had an office building. It could be now converted to educational building now. It could be an hospital. It could now serve as an auditorium for some kind of a gathering, assembly area. So in that case, you have a major change of live load, and also you could be bumping up your risk category. Your risk category could be going up. And this is one of the major changes that triggers the need to evaluate the existing buildings. The last type is the addition. So what additions means is that you're increasing the floor area. You could be adding more floors, or you could be extending it horizontally. In both cases, you are basically, again, triggering a requirement to check your building. And what the typical cost involved on the last column I'm trying to show is that it's a very general based graphics, basically just tending to show that in terms of the code requirement for the code, how much you need to check. Do you need to check just a local area? For example, you have a building of 10 bays by 8 bays, and you're doing, there's a live load change just in 4 bays. Do you need to check your entire building, or you just need to check that bay where the live load change occurs? It really depends upon the nature of the work. And the intensity of the work that would trigger. It might not trigger the entire building analysis, and it might. So that's why we have a typical cost involved. So for the repairs, it's usually just rectification. In case of alterations, if it's a very major alteration and you are triggering, then the cost would definitely increase. If it's a change of occupancy, and because of the change of occupancies, it's not just a change of the gravity load, but you also have changed the risk category. Now your seismic loads have bumped up. So that means you need to look it into from the seismic perspective as well. The last addition is typically the most expensive one, because when you are doing additions, you typically adding quite a lot of load on your structure. So this summarizes the types of work. So jumping to the next slide, I just want to quickly go over this thing and summarize what we talked about. For example, there's a maintenance or rectification work happening after the hazard. There was some hazard you're rectifying. So it's going to be, the type of work is going to be typically repair, but it could be an alteration as well. If, for example, if there's some major change that you need to do after the hazard. And the type of evaluation would be mandatory. For example, the earthquake hit a certain region and the building is in pretty bad shape. So the building department would instruct you to fix your building and bring it up to a certain safety level. So it's a mandatory in that case. If you're mitigating some strength or stiffness issues, it's an alternation that you're doing. And again, it could be mandatory or it could be voluntary. If it's coming from the building department and it's mandatory, if the owner is doing himself, it's a voluntary. If it's a change in the live load, it's an occupancy change, right? In the code language, and it's triggering, it would typically trigger the evaluation because of the increased loads. So the last type is of expansion. So what expansion means is it's an addition, right? So addition could be, again, it would typically trigger to check the entire building for the seismic, and you need to at least check the members that have increased gravity loads for the gravity. But for the seismic, you would typically have to check the entire building in case of major increase in the seismic mass. So this is like a building I wanted to show. So we've been talking about words. So I just wanted to show you a picture what we are talking. So you would see in this kind of buildings, you see the bottom 2 stories is a concrete frame building, and it was constructed in 1922. This building is in New York. It's called Carey's Building, and it's a pretty famous building where they actually studied the on the existing buildings. So what happened is they had these 2 stories of which were already there since 1922. They made 1, 2, 3, 4, 5. They made 5 stories above it, 3 full stories, and 2 partial stories above. Now, this kind of condition, when you have this kind of condition, basically you have increased loads on your building. So you need to check the building below for the increased gravity loads. And we also have an increased mass that's now sitting on top of our existing building. So we need to ensure it's not just the increased dead and gravity that's there, but also the increased mass and how that force needs to transfer out at the connection points. That typically is a very important thing in case of existing buildings where you have this new mass that's on the top, and you need to make sure it transfers out right and it's delivered to the foundation. Like the load path needs to complete. So what I show on the left side is that when you have a new addition on an existing building, what the code would say is that the new addition needs to be designed as per the new code, and the existing structure that's sitting below needs to comply with the IEBC, basically. I think it's pretty straightforward from here, and I'll go on the next example. So the next example shows you something that would happen. There's a building, for example. Now the owner wants to repurpose their building. You will see all the architectural cladding, the ceiling, the floor finishes would come off, and there will be also a change of the door and windows also, right? So this could be a major alteration, or this could even be an occupancy change, depending if they are changing the intent of the usage. So when something like this happens, it does trigger the requirement to check the members for the increased loads, if that's the case, and check the members for the increased seismic loads, if that's the case. But if you're decreasing the loads, basically you are not triggering the need to check. And this is the interesting part of the existing building code, that it wants the owner to keep using the building. It doesn't want to like penalize you, that because you own a building that's 30 years old and now you are penalized because you're doing so and so. But that's why it wants to give the relaxation that you can keep using it, but you need to meet a certain level of minimum safety levels. So let's now talk about the challenges that are associated with existing buildings, especially the retrofit works. The first thing is that there needs to be a feasibility of the retrofit work, right? The retrofit cannot be more expensive than the new construction. If you are retrofitting a building that's 6 or 7 story high, and the proposed retrofit surpasses like the construction of the new, it typically doesn't even make sense, because the owner can just make a new building out of it. So the retrofit needs to, like the cost needs to make sense in comparison to the new construction. The second thing is that in case of existing buildings, we need to minimize our disruptions, and we need to work in restricted spaces. In case of new buildings, we're usually working under open sky. We have a lot of area that we're working in, right? But in case of existing buildings, you are restricted by the buildings in the neighborhood, and not just that, but also you are typically working inside the building. So you don't have the same headroom to work with. And that's why I've seen a lot of existing buildings where we would use micro piles to retrofit where we introduce new shear walls, because they require less headroom and less work. You might not be able to do the typical piles inside existing buildings because of the headroom issues, and because it needs a lot of space to work around it. So there are like several things associated with existing building, which limits your options basically. The fourth challenge is that you could be just missing the drawings. You will not have the drawings for the existing building. And if you are analyzing a structure and you don't have an existing drawings, you basically need to establish the drawings first. You need to establish the as-builts. The fifth challenge is that when you're working with historic buildings, basically, we need to again maintain the character of the existing buildings. And this is also addressed in the existing building code. We cannot change we can typically not change the facade, and we cannot typically change features that are associated with its historic character. So we need to bring the performance up, but we also need to make sure that it does not change the overall look or the character of the building. And the last challenge, major challenge associated with existing buildings is that how we connect the existing and the new members. This was the item that I was talking about earlier as well, because in the new construction, especially in case of concrete, the joints are monolithic, right? You cast the concrete around the joint once, but once we are doing some additional work, you are expanding an existing structure. Now you would have to use, for example, drill and epoxy anchors. You would have to use expansion anchors. You would have to use some other solutions to connect the existing and the new members. So this is also one of the challenges of working existing um, infrastructure. So this is a brief slide that I don't want to get really boring with all this history stuff, but what I want to show is that existing building code is the understanding of existing building code is even relatively new in the US as well. It's not same as the new code. The new code has been there from as early as 1900s. If you try to start with when US started to develop their building codes, you would find documents and ordinances uh, that it predates even the world wars. But in case of existing building codes, they have this problem now. They developed a lot of infrastructure, right? It was standing already there. Now the challenge was how can you encourage the owners to keep reusing it? You don't want to penalize the owners that, oh, because you have a building that's 50 years old, now you need to bring it up to the new code. And if you cannot bring it up to the new code, then you cannot use it. Because if they would start doing this thing, then the cost of the retrofit not justify itself. And also it will discourage the reuse of the buildings. So I would break it down to the code provisions between pre-97. But pre-97 they had is that pre-97 the trigger was correlated to the cost of renovation. So if owner had a building and they was doing some renovation, which the cost of the renovation was deemed to be approximately 50% or more, they would say that your building needs to comply with the current code. So that was a huge penalty on the owner, because that means that if you're going to renovate your building, or you are selling your building to someone else and they want to reuse it for another purpose, then they would have to bring it up to the new code. That means that they would have to spend a lot, not just on the renovation, but also on the retrofit works. So that changed in UBC 97. So UBC 97 abandoned that concept that if you're spending so much, then you need to bring it up to the new code. But UBC 97 did is
I think we have a technical problem at our speaker's end. I think the speaker has got disconnected. He will come back again and he will start from where we lost the connection. Let's give him a little bit of time, 2-3 minutes. I think he should be able to come back.
sorry for the inconvenience. I had a issue. Can you, Tarsa, can you hear me now?
Yeah, we can hear you now. Please go. Please start from
Okay.
where you.
Okay. Okay. I hope my screen is displaying right now.
Yeah, all is
So,
well. Kindly go ahead.
okay. Thank you. So we were talking about how the code started to change, how it changed its perspective. The code language was in a continuous state of evolution in terms of how it viewed the existing buildings. And what happened is that the existing building code actually came out in 2003. Even in the IBC 2000, they had like few pages towards the end, I think, to how to handle the existing buildings. And I think Building Code of Pakistan 2021 is actually our first code that addresses existing building. And I think it's in the Appendix A. I think I saw it, if I'm not wrong. But so US had a similar start, but then in 2003 they had an entire new book, an entire new code in IEBC 2003 for the existing building. And since then they had 2006, and now it's in 2021 version. So what has happened over the period of time is that now you would see that the existing building code is pretty detailed, and it caters to the requirements of the owners. That if you're doing certain so and so work, then you need to check for this much, but you don't need to check for the entire building. So it's now pretty detailed in terms of addressing to what could be happening to an existing building. So, and there is like a statement that I wanted to show from a white paper from the National Institute of Building Sciences that very nicely summarizes the intent of the existing code. So what it says is that the purpose of existing code now is that you want to capture the maximum benefits out of an existing building code without penalizing the owners and giving them incentive that, okay, so that you don't want them to bring it up to the new code always, because that would not just work for the economy and it would never work. And the cost to benefit ratio the cost to benefit ratios need to make sense. So this is the basic intent of the existing building code. So moving on, moving on to the next slide basically shows you there are like two different codes, right? You have IBC, which is for the new anything that's being constructed new. And what's already in there from before, we have the International Existing Building Code 2021, which is the latest version of it, and it refers to 4117. So just like the IBC refers to 716 for the loads, IEBC refers to 4117 for the loads. And I will go over the detail what this means and how this is handled. So the intent, like I discussed, the intent of the IBC is that if you design for a certain prescriptive based approach, for example, you attain a certain level of safety. You're deemed that you will attain a certain level of safety over the spectrum. You can design above the IBC as well for your new buildings. That would be going above the code, because the code IBC is the minimum requirement document, right? But what IEBC does is the existing building code, in typically cases, it's slightly below. It is supposed to be slightly below IEBC usually, but it does go in the same in the same range when you are basically triggering the full building analysis because you're increasing the load too much or decreasing stiffness. But if you're not doing so, your safety would be slightly lower, right? But the reason for this is because the existing building does not have the same lifespan of a new, and the retrofit needs to make sense in comparison to the new construction. So this is a brief to tell you like how IBC and IEBC are even different in terms of how they view safety, basically. So this shows you these snaps are taken directly from the building. codes. And on the top, you see is a snap from the IBC. On the below, you see IEBC, the existing building code. And you see it's from chapter 1. You see it says on IBC, establish minimum requirements to provide reasonable level of safety. But if you see the next IEBC, it says provide flexibility to permit the use of alternate approaches. So IEBC is actually is not divided, is not structured the same way as IBC. If you open the existing building code, you would see that it's structured based upon the nature of work you're doing. If you're doing repairs, you just need to check this and this, and you're good enough. If you're doing alteration, depending upon what's the nature of the alteration, you need to check this and this, and you're good. So if IEBC provides you the flexibility, and it also has the prescriptive based approach, it has the performance based, and it also has the work area based approach as well. So there are like several approaches even in covering different natures of the work. So this is another like the snap from the codes directly that I took from the existing building codes. And what these two snaps does is it shows you the two analysis approaches inside the existing building. What you see on the left side is, you'll see it says you need to comply with the full seismic forces. And what you see on the right side, it says voluntary alterations. So like we talked about, if in case you're doing something very serious, so if I label this as 1, this column, and this column I label is as 2, if you're doing something very serious to the building, there's a risk category change, you are upgrading the risk category, you're increasing the loads too much, then you need to comply with the full seismic forces. And IEBC would tell you to do ASC 41 Tier 3, which is a full building analysis, or it still gives you an opportunity to use the IEBC and ASC 7. And that's pretty interesting. That the reason they still have this clause in here is that not the usage of IEBC or existing building code is still not very well understood across the industry, even in United States, and it's even lesser for building officials. So they still want to give you a liberty that if you could justify the current code application over the new code, it's on the existing building, then it's still good enough. But what typically engineers would do who do understand the existing building code, that they would use ASC 41 Tier 3. Because it will give you more advantages of reusing the frame members, which otherwise would not even fall under intermediate or special movement frames. That's what. So the second column shows you the voluntary seismic retrofits. So for example, you're not altering too much, you're not making anything very worse. So if you might be able to use a voluntary seismic retrofit approach, which means you can retrofit as required. You can, but you should not be making the building worse. You cannot introduce you cannot introduce a torsion irregularity. You cannot decrease the capacity of your members by a certain limit, and you cannot decrease the stiffness or strength of the structure. So if you're not doing it, you're making it better, you can do a voluntary. By voluntary means you don't have to check, you don't have to ensure that the entire existing building complies with the current code. You don't need to do that if you're not making things worse. So I'll remove these marks from this slide before moving on to the next slide. Okay, so what the next slide does is basically it gives you one-to-one comparison of the basic differences between ASC 7 and ASC 41. Now we're moving into the analysis and the loads. So what ASC 7 is basically, it's a prescriptive based design, right? We know that what ASC 7 would do is that it does not give you the liberty to design for several performance levels. It has one performance level basically where you're designing for your design-based earthquake, and that's the life safety. So you have the loads that you compute, and based upon the loads, you get your demands. You get your shear demands, moments, torsions, and or you're checking for certain serviceability checks for the deflections or deformations. Not the deformations, it's actually the deflections or the story drifts. And you compare it against the allowable limits that are inside the ASC 7. And if you're complying with that, then your design is deemed to be going to perform okay. But what ASC 41 has, it does not have the prescriptive based design. It does not have it even in the linear approaches. You can use the performance based design even with linear approaches. This is like I was just talking to a few of my colleagues, and I did understand that the performance-based design is the theory behind that is that you design to certain acceptable damage levels. You select your hazard. You are given some options to select from. Then you have your allowable damage that you can design to, and the composite of that gives you the performance matrix. But you can even adopt linear approaches to work with that in the case of ASC41. So the second difference is in ASC7, we have this global dictability factor of our R, right? Our usual friend factor R that we talk about so much. Like, for example, we have a different R value for special moment resisting frame. We have a special one for the intermediate and a different one, lower one for the ordinary moment frame. But in case of when you go on ASC41, there is no R factor. Although you are doing a linear analysis, there is no global R factor that you can assign to your structure. So the basic theory behind ASC7 when they developed this R factor was that they did extensive lab testing on moment frames with different, for example, with different confinements and different properties of the reinforcement. And then they established this R factor as a global factor that you will apply over your entire structure. But what ASC41 does is that you will still use your, you will not reduce your seismic demand by the R factor, but you have M factors that you will use, and those M factors they vary by members. So there's a different M factor for your beam, for your column, for your joint, and everything. So it's a component-based approach. It's not a global-based approach. And this is another difference between linear approaches adopted by ASC7 and ASC41. And they have a J factor to counter for the members that are intended to remain elastic. So you have, for example, you have columns that support a discontinuous shear wall, or you have a member that you do not want to show too much of an inelastic behavior. So you would not use an M factor on it, you would use a J factor on it. I don't have the liberty to go in detail, but my basic what I want to explain is like there are no R factors inside ASC41. You would see M factors and J factor there. So what ASC7, another thing about ASC7 is because it's a prescriptive based approach, and what it does is that it handles all the actions for axial shear movements are handled the same way. Like you get your demands, you compare against the capacity. So the structure is deemed to behave okay. But if you go in ASC41, it classifies even the actions differently. So it says your shear is more important than your flexure. So your member should not show too much inelasticity in case of a shear action, but your member should show flexure hinging, right? So if you want your member to show flexure hinging, it's important that you have enough shear reinforcement that the member does not just like shear away before the flexure hinging could even occur. So ASC41 first breaks it down to the member components, and then it even further breaks it down to the action and components. It handles even the components separately. So this is like a very simplified and very quick way of understanding what performance-based approach is, that you have a ground motion that you select based upon a probability of exceedance, right? In certain years you have, and then you have a performance level, which means that the maximum damage the acceptable damage that you are willing to take after a major event hits. So when this event hits, or an event equivalent to this, basically. It's just a mathematical model, but when an event equivalent to this hit, I am okay. Like the owner says, I'm okay to have my structure damage approximately till here, right? So with this, when you select this and this, it becomes a performance matrix. And the way code gives you the performance matrix is that based upon risk categories. So if a structure is more important, for example, you have a hospital, you have a fire station, or the structure, or like the school buildings, which should stay operational, or there's a major life hazard in there, then your performance matrix would give you strict criteria for that, and it would be much relaxed in case of buildings that are not that critical. So moving on to the next slide shows you the response spectra plot. I just took this values from USGS tool online, and I just plotted it for different hazards that are basically available inside 41 for the downtown area of LA City. So in ASC 41, as you can see on where my cursor is right now here, we have 4 kinds of hazard. We have BSC 2N, BSC 1N, BSC 2E, and BSC 1E. So we have 4 different kind of hazards in ASC 41. That's another difference from ASC 7, where we just have one response spectra to play with. And BSC 2N is actually here, the red one on the top. And you can see this is actually equivalent to MCER, maximum considered earthquake with the risk of 1%. And when you take 2/3 of it, you come here to the blue line, which is BSC 1N. So this is 1N, and on the top is 2N. And what 1N is, it's just like a 2/3, which is equivalent to a design level earthquake that we use in the new code. Basically, it's equivalent to that. And what BSC 1E and 2E and 1E is basically, it's this yellow here and this green here. So the green is 1E and the yellow is 2E. So like I said, that existing building code understands that you don't need the same safety levels every time. So they introduce these new seismic hazards, which are actually 75% less, sorry, not 75%, they are 75% of the hazards used for the new code. So you have BSC 2N, let's say this is 2 point, let's say 4, let's say, right, on the top. And I'm just saying in a very crude way, but the way they establish BSC 2E is that it drops down here, and now it's just 75% of the hazard. So you would see that you might not have to use the higher hazards for your existing buildings. You might be okay by using BSC 2E and 1E. But it really depends upon the nature of work, like how much you're triggering your building, how much you're making it worse, or what's the nature of the work. So there are like 4 kinds of hazards that are given by ASC 41. So now we will talk about the next slide. So next slide basically summarizes the last 2 slides that we were talking about, the hazards and the performances. So what you see on the bottom right is the performance levels basically. So if the owner wants that right after a major earthquake hits, they want their building to still stay operational. Now this is a very strict criteria, right? So if the owner if you select this criteria, then you mean you want an operational level. What immediate occupancy means that there are some minor non-structural damages, but there are almost no structural damages, and this is immediate occupancy. What life safety means, performance level means, is that there have been substantial structural damages, and there have been even more non-structural damages, but there are no life safety hazards in case. And this is what the ASC 7 actually designs for. ASC 7 designs for life safety here. It's embedded inside the code. You might not, it doesn't say it explicitly, but that's what embedded inside the ASC 7. And what the collapse prevention means is that the building skeleton is just barely standing. Like it has not collapsed, but pretty much everything else has happened. Even non-structural components have failed. So these are like the 4 performance levels that we have an option with. And then you have the hazards that we already talked. So the approach would be that you select a matrix, you design your building to comply with that matrix, and you'll keep iterating it till it complies with that matrix. And once it's done, then you have your retrofit drawings ready to go. So this is another slide that quickly tells you that if you select the question is going to be why. So if immediate occupancy is the best approach, right? It means a major earthquake hits and you have the least damage that happen. And in case of, for example, collapse prevention or life safety, you have the most damage there, right? So the question is going to be, why don't we just pick the immediate occupancy for everything? But the answer to this thing is you cannot because it's going to be so uneconomical to design for such a stringent approach, for such a tight approach. It's not an option. That's why even ASC 7 designs for the life safety approach. And but what's the benefit? For example, there's some a commercial, let's say, building that's 10 to 12 story, and the client has a lot of, let's say, money to spend. And they said that I don't want my building to go unoperational even for 30 days after the earthquake. So what he would do is that he will ask the structural designer to go above the code and design for a performance level that's even much better than what the code is saying to use, right? So what would happen is that they would have minimum replacement work. So if you pick a better performance level, your replacement work would be even less. Your chances of any deaths would be lower, and your downtime means that your building can come into operation right after the earthquake, or let's say few days after the earthquake. So this is the basic theory behind the performance-based approach, that it gives you this liberty to choose from different options. So what you see on the next slide is basically two performance matrices that are inside the existing building code. And what you see on the left side, it says if you were doing full seismic forces, which I think I talked about this a few slides back, then in case you're doing some major alterations to the building or some major changes happening, then you need to pick this matrix. And when you come in this matrix, you will see, unfortunately, I would say you will see PSCE 1 and 2. So you have much higher hazards if you fall into this matrix because of the nature of what you're doing. But if you're not making your building worse and there's some minor alterations or there's some alterations happening inside the building, then you can use this matrix, the one on the right hand side, which is the equivalent to a BPOE inside ASC 41. You see BSCE 1E here and 2E. So these are reduced hazards. They are not the same hazards that are used by the new code. So under the matrix, I took these lines from the code actually, that if you have a change of occupancy or you are having additions that are happening, then you need to comply with the matrix that's in the first column. But if you have alterations, typically you would fall under the second matrix, which would be with reduced hazards. Just let me please remove these marks from this slide. So let's now see how ASC 41 classifies the elements, right? You have a building, beam, column, slabs, you have diaphragms, you have shear walls. So now let's see how ASC 41 classifies those. So the first approach in ASC 41, you will see they classify as primary and secondary members. What a primary member means is that it's the member that is supposed to resist the seismic forces primarily, right? So it's your shear wall, it could be your moment frame, or it could be any member that's supporting your discontinuous shear wall or discontinuous moment frame. Although a discontinuity is not preferred, but for some reason you might have it. And the members that are gravity members are shown in blue here. So they are classified as secondary. So ASC 41 does not have the same criteria for secondary and primary members. So the primary member needs to be checked for much strict criteria, right? Because those are the members that are taking the seismic forces. And the concept for gravity beams and gravity columns is that they need to have enough capacity that they can accommodate the deformations, because the gravity beams and gravity columns does not mean that they're not going to see any seismic forces, right? They would see something, because when the building is going to sway, they're going to have some deformation. So that is why you would see that over the period of time in 31819 ACR 31819, when you have SMF or you have this high ductile frame structure, they will still give you sometimes they would just point to a very strict criteria even for your gravity columns. And the reason is that they understand that those columns also have to undergo sufficient deformations due to deformation compatibility. And the second classification that's inside ASC 41 is based, like we talked about, is based upon a force-based member or deformation-based member. So the members that you see on the screen on the right-hand side in green are deemed to stay elastic during the selected hazard level. And the members that are in brown, they can undergo sufficient inelasticity. So you want your shear wall to have the energy dissipation. You want your collectors to have the drag beams to have the, but you do not want the connections to show any inelastic behavior, right? We saw the pictures on in the very start of the talk. We saw the joints opening up and energy dissipation being concentrated at the joint. So that's not something what ASC 41 wants. So it would tell you to design the connections and any columns that are supporting a discontinuous frame structure to be designed for much higher forces so that these members do not show any kind of inelastic behavior or very little. You want your deformations to be concentrated over in the members which are reliable basically for inelastic behavior. So ASC 41 has different approaches to analysis, and I'll go fast because I think I'm running out of time maybe, but there are three approaches. There are tier 1, tier 2, tier 3 approaches. And the first approach is a screening based checklist that you have a building. They have different building types. You have a checklist that you will check that, okay, based upon their prior knowledge, they know that concrete frame buildings with infill bricks shows these kind of deficiencies. So the first way is that you just check through the checklist. And if the checklist shows some non-compliance, then tier 2 would help you to rectify that deficiency. The tier 3 is the full building analysis where you basically have to model the entire building in ETABS and check all the members, basically. But it's important to understand that if you're using ASC 41 for existing building, it does not mean that you have to model your building in a software each and every time and check everything. That's not the intent every time. You might be required, but you might not be required every time to do that. So what's like the line of action before starting an analysis, right? When you start an analysis, the first thing that you need to gather all the relevant documents. You need to get the existing drawings. You need to get the geotechnical reports. These are important before starting analysis. Then you need to establish the history of the construction and modifications, if any. So when you're analyzing an existing building, if you're just sitting on the computer table and start modeling it and you start the analysis and you say it's okay, it's not okay. It does not have a meaning to it unless we know what's the history of construction and modifications that have happened over the period of time. Then the third case is that we need to conduct site visits, take photographs, take field notes, and document any defects, anomalies, or deviations that could be seen from the drawings. So this is like the something that's really, really important for existing building analysis, and it needs to happen before the analysis, or otherwise, like the analysis is actually not is not good enough. So I'll just go quickly through the flow chart. This is like the flow chart that tells you, I took it from the appendix of ASC 41, I think was B, and it tells you like the flow chart of how you'd start your analysis. So what 1, 2, 3, 4, 5, what these 5 would say is what I already talked about, that you need to first understand your performance levels, performance objectives, what's like the seismic hazard, and establish the performance metrics that we talked about. Then you need to get the as-built information, site visits, existing drawings, material testing, whatever you need. Then you have two options. Either you go into the tier 1 checklist or just do the checklist and be okay, or you need to do the modeling. It really depends. Now, ASC 41 did not used to have such stringent thing, I think in 13 and before in 06, but now since 17, they've been more strict in the usage of tier 1 checklist. Now, what do they say is that if you have a building that's too high, or it's in a region that's a region that has a very high seismic region and the risk factor is high, then you should not be using that checklist approach. You need to do the analysis approach. But then there's a table inside. You can read this section and you will know that if you can do tier 1 checklist or not. But whichever way you pick, the end result of an analysis to ASC 41 is going to be an evaluation report, right? So you need to submit an evaluation report that will document the original construction. It will document the history, anything that's happened in the past, renovations, retrofits, defects that you saw on site. And then you need to incorporate the analysis results that you have. And towards the end, you will provide some schematic sketches or proposed retrofits that you think need to be done to rectify those deficiencies. So that's like the crux of the analysis of ASC 41. So this image just shows you the snap that I took from the tier 1 checklist. So there are like a lot of checklists on the tier 1 checklist on ASC 41, and it pretty much depends upon the two things. So one is the performance level, which is collapse prevention here, and the building type. So building type, the snap that you see below is for a concrete movement frame with infill bricks, which is the common case for in the case of our country. So you will see that this kind of checklist you will see in ASC 41. So when you read this item, you need to go like this item by item. You need to see, are you complying? You're not complying. It's not applicable to your building. It doesn't fall, or it's unknown. You don't have sufficient information to establish this. So based upon this, you need to pick one of these 4 options for the entire checklist. So this checklist is longer, but I didn't want to paste the entire of it, but that's the crux of it. And if you have a non-compliant, let's say you did some quick shear stress check and you are non-compliant on the checklist. So what you need to do then, you see tier 2 reference here, you need to go into this section and it will tell you what needs to be done to rectify this deficiency basically. So that this is like the very basic level understanding of like how the tier 1 checklist works. And they're like different, like I said, there are different checklists for different structural types. So the next question is, how do we select a retrofit scheme, right? So the first thing that we need to understand is like, what's the original construction? When you're doing a retrofit, the first thing you need to understand, are you working, is the original construction steel or is concrete, or what type of construction it? Because the retrofit needs to be accordingly. The retrofit for a steel building, it's not going to be the same for the concrete, and vice versa. Then you need to understand what's the intent of the retrofit. Why am I retrofitting? Am I retrofitting just because there is some, let's say, they are putting some heavy transformer on the roof and I just need to retrofit the beam? Or there's an occupancy change, there's some major change and I need to retrofit several things, right? So you need to understand what's the acceptance criteria. What are we retrofitting for? And the retrofit would really depend upon that. The third thing is that we should always try to minimize the disruption in case of retrofit works. That's very different from new construction. You can have your shear walls spread over the entire building, but that's not typically what you would prefer for a existing building retrofit. You don't want to spread your work over the entire building, because then you would have to open several spaces and work with them, and then the cost would just rise exponentially. The last point is that the retrofit, as we talked about, needs to justify itself in comparison to the new construction. So I just try to close it up in 3 to 4 minutes now. So now what we see here are the typical strengthening details. So these are not for every case of work that you will see, but it just shows you like a typical case that you will do. So if you have an existing concrete column that you see here on the elevation, and you want to retrofit it for example, increased axial loads, let's say, right? Because this retrofit detail actually does not cover the joints. So I would not say that it's a retrofit detail for increased movement capacity at the joint. So I would just say it's an increased axial capacity for now, although it does increase the movement, but not at the joints. So what you would do is that you have this original section that you see on one, then you would chip away the cover so you will just chip away the cover and you will clean the rebar that's exposed now. And you would roughen up the concrete surface so that you can make a good bond with the new concrete. Then you would insert the dowels through drill and epoxy. I mean, there are several brands, but Hilti is like the most famous one and commonly used. So you'll do these epoxy dowels, and the purpose of these epoxy dowels is to make a good connection between your existing and new element. And I'll say this thing here, that these dowels are extremely important. The reason is that you can provide as much more rebar outside. You can expand your column as much as you want, but if there are not enough dowels that are connecting the existing and the new expansion is almost meaningless, to be honest, because you need to have enough connection between the new and existing that the force that those two new and existing can act as one. So the last thing that you see on the screen, the 6, is how your section would look towards the end the retrofit would look towards the end. So now I'll jump to the beam strengthening detail. So the same thing, for example, if for some reason you need to strengthen your beams, so what would happen is that if you could see this cross section here, you see the outline of the existing concrete here, right? So what again, you try to chip the cover away. You will clean the rebar. You will make the existing concrete rough so it can make a good bond with the new concrete. You will have your formwork and the rebar. You will erect your formwork and then you'll put the rebar around here and increase the width and the depth as required. You need to have your drill and epoxy anchors. Again, these dowels need to be there so that it's a composite section. Without enough dowels, the added rebar on the bottom means nothing. And then you need to add this shear bars I would call the ties so that you can connect everything together. And you can just drill it into the slab and stop if the slab is thick enough. Or if the slab is not thick enough, then the drill epoxy embedment length is not going to be enough. So then in that case, you need to pass through the slab, go on the upper side, and you need to anchor it somehow on the top. So, but this happens when the slab is too thin and it does not have enough space for the embedment. So this shows a typical for the beam. I want to show this image of a beam, introduction of a beam. For example, there is some increased load or there is some change happening. So you add a new beam in the existing bay, right? So you see what you see here are, you see these horizontals here. This is the positive steel. For example, let's say it's a gravity beam, right? It does seem to be a gravity beam because it's framing into an existing beam here. It does not seem like a frame beam. So for the gravity beams, you calculated, okay, for here I needed this much positive rebar. So you provided this positive rebar, like here, you might be designing 2W L square by 8 or whatever, but depending on your end conditions. But you do the positive rebar here, then you need to connect it back to the slab. Again, these dowels are really important because without the dowels, this structure cannot act as one with what's already there. So this shows you how typically new concrete beams could be introduced. I mean, you could be introducing steel beams as well. And then with the steel beams, you would have an end plate on the ends. And then you would do, like, for example, you would do an end plate here. And you will do a flange section, an ice or flange section, and then you do epoxy dowels or to pass through this beam. So it could be a steel beam or it could be a concrete one, like shown as well. So the last slide of this presentation shows you like a retrofit for a slab opening, right? So again, you might not need a retrofit for a slab opening if your opening is too small, right? I'm just showing a typical case. For example, you're cutting too many rebars. For example, you have a slab opening that was introduced here. And now there were some positive bars going like this. There were some positive bars going like this. Maybe there were some negative bars as well close in that you cut here. It really depends upon the detailing and where this opening is positioned in reference to the support conditions. But so once you lose the positive and negative rebars, you need to supplement it depending upon the requirements. With supplemental, what we would do is like we would have these steel plates that we will bolt below the slab. And we might have to bolt it above the slab if it's a negative reinforcement requirement. So it's very important to understand, for example, if your opening is, let's say, too close to the column, right? And you lost some positive and negative bars. And then if you put the plates on the bottom, it is meaningless. Honestly, it's meaningless because you lost the negative reinforcement. Then you can't. I mean, you're putting the positive reinforcement there, but I mean, you might say it might be said in terms of the moment redistribution theory or whatever, but the concept is that if we are losing the negative reinforcement, then we need to provide supplement accordingly, and if we're losing the positive reinforcement, then we need to supplement accordingly to ensure that it stays in its original intent. With this, I would like to end my presentation and thank the Society of Civil Engineers. I would like to thank Tahir Saab, especially for giving me an opportunity to present here. I'd like to thank all my seniors and Rizwan Saab, especially for inspiring me to give this talk. I end my talk with a quotation that words may inspire, but at the end of the day, it's the actions that we do that create the change. Thank you.
Thank you, Rehan, for such a detailed insight on the topic. And I hope our audience have also enjoyed the lecture, and they must have learned, the young engineers must have learned from your detailed insight. And now we come to the question answer session. I have 5 questions in the chat box, which have all of them have come from Rizwan Mirza. And there is one more question just coming in. Let me see it. Okay. Now, we had audience on Facebook also. So there is one comment just on the Facebook. So I will just start with that comment. And Rehan, you can listen to the comment. I will read it out for
Yes.
you. If you
Yes,
have
thank
anything to say, you can say it. Otherwise, it is not a question. It is just a comment.
Ji.
This comment has come from Sayyid Qausar Ali Shah. He is saying retrofitting is a civil engineering challenge where in Pakistan, the most of the engineers are not familiar and having less knowledge of it. So if you want to comment anything, please go ahead.
I'll just pass on this thing. I think it really depends upon the engineers. There are a lot of people who could retrofit properly. There could be people who do not understand it right as of now. So it's relative. I wouldn't pass a blanket statement.
Okay, thank you. Now we start with the questions one by one that I have received in the chat box, and we start with the first 5 questions are from Rizwan Mirza. The first
Ji.
one is, Rehan, if you want, if you can open the chat box, you can also see the question, read the questions yourself, but I'm going to read them aloud so that everybody can
Okay.
hear.
Okay.
Question number 1 is, any intervention in the existing building in Pakistan would potentially have far-reaching legal overtones. With the current legal framework of the country, what course of action would you suggest?
It's a very good question, and this is the problem where the existing building code in United States ran into problems several years ago, because we don't want our buildings to be just flagged. Like, oh, this building was constructed 30 years ago. Now all of these, like several buildings are going to be flagged, and then you need to bring it up to the new code. To me, it would not make any sense, because we need to first identify what's more critical, what has a higher risk associated with fatalities, because we need to understand that there's a difference of economies, right? If you propose a solution to everyone that, okay, so your downtime for your structure after a certain retrofit would be 30 days. I mean, he cannot afford it. He doesn't care about it because he doesn't have the same finances. So I think what the question is basically asking is, I know it's a very delicate matter that we cannot flag all the buildings right away by saying it. But I think the way would be that all the stakeholders need to come together, and there need to be several discussions before anything enters the code. I don't think anything should be added into the code just because it's happening in the developed part of the country without a proper discussion.
Just a second.
सर ये ना इसके बाद अभी जैसे ना आपसे डॉक्यूमेंट साइन करवाने बैंक के तो वो कर दीजिएगा मैं उसको देके जा रही थी
Okay, now we have the second question. It is again from Rizwan Mirza, and it is, you mentioned 2005 Kashmir event, the Kashmir event. What, in your opinion, were the key factors that determined the disastrous fallout?
So there could be several opinions, but my very humble and very brief opinion would be that design is one aspect. What we design to is one thing. The quality of construction and the workmanship is a totally different chapter. We could be focusing on the forces, on a lot of things, but if the quality of the construction is poor, as the images I showed, I mean, although we had UBC 97 at that time, when the 2005 earthquake hit, still UBC 97 did not say that you should have these kind of joints in the northern part of the area, in the country, right? So just the code itself wouldn't do the job. It a lot has to do with the workmanship, quality of the concrete, the ties, the hoops, and how all that detailing is happening. So I think it does have to do with a poor understanding of soft stories, with a poor understanding of the importance of confinement, especially at the joints and inside the columns. But it also has to do with the construction, with the nature of the construction that has happened all over the Pakistan.
Okay, I think you answered the question very well. In my opinion, I mean, the major fault was on the design side, and plus also on the detailing and how you had confined your reinforcement. Well, I think major reasons were told. Anyhow, we jump to question number 3. Codes do not permit unreinforced masonry in moderate seismic zones. The post-2005 solution for future buildings that you alluded to apparently still has unreinforced masonry. Would these proposed structures be considered code compliant?
If we are looking in terms of the American codes, then it's not, because in American codes, these, like when I was displaying that picture of the solution for the unreinforced masonry, I mentioned that these solutions are developed in Pakistan and India, because we were still using these walls as for partitions or for the exterior, but they are obsolete in the developed part of the developed part of the world. So if we say it's pretty unfortunate that we do not have a very easy solution because of the financial reasons. But the best way out of these would be that we would abandon these brick walls and go to the dry walls and light gauge walls with drift joints, so that that would perform much better than these.
Okay, now we have question number 4, again, still on Rizwan Mirza. There is now an attempt to adopt seismic events with a 2% probability of exceedance in 50 years as a basis for design in Pakistan. Do you find designating such events a basis for design consistent with our economic conditions? It is an economic and social question as much as is a technical, isn't it?
I totally agree with this approach, but it needs a lot of discussion. It needs a lot of discussion from a lot of quarters. I feel like I feel very humble to respond to this, and I don't think any single individual can actually give the entire solution with this thing. There should be discussions between the structural engineers with the stakeholders, all the stakeholders that are involved in the construction industry, to understand like how much damage we want to accept for our buildings. Because I agree that we cannot have the same allowance as the developed part of the countries, developed part of the world is having. So I agree that we need to have more discussions on what's like the acceptable allowance for collapses.
Question number 5, still on Rizwan Mirza. Would you agree that in Pakistan, the major issues are code enforcement, capacity issues of structural engineers, and level of ethics generally adopted?
I It's hard for me in this position to say anything, but I would again say that the understanding the code is like basically for us junior engineers especially, it's the most important thing. It's the first book that we should be reading. It should be the code, but the code on its own cannot resolve everything, because a lot of the construction that has happened in Pakistan is not code compliant. And the codes that we use, the American building codes, are as per their like type of constructions. So it's very important that we read all the papers and everything that has especially been directed towards the type of construction that has happened in Pakistan and how it has performed. That will really help us to understand, like when I'm designing a brick infill frame structure, how it would behave. Then I would be doing something maybe above the code that the American code cannot handle, because the American code does not know that you would have an infill brick in your frame structure. But we cannot do that unless we have an understanding of all understanding that has developed by reading all these papers out of the 2005 earthquake and everything that has been developed, especially in the South Asian part of the world.
Okay, now just one clarification I have to give. There's a few questions on Facebook regarding your lecture. That is this lecture would be available? Is it possible to get the video of this lecture? As Rafiq has asked, this lecture would be saved on our website. Let's say after in a day or so, you would be able to download this lecture from our websites. And there are other lectures also which were delivered. You can always download from there. And if you cannot download any of the lecture, then there is a restriction on it for downloading it. Otherwise, most of the lectures you can download from our website. So this was the clarification. And now we come to the question from, this is the question from Muhammad Azim. How much is CFRP wrap? How much is CFRP wrap are effective in beam and slab retrofits in Pakistan? If CFRP is not applied correctly, and bond failure can result in ineffective wraps.
Okay, so this is an interesting question again. So we have a lot of vendors that are selling different solutions, but unfortunately, we don't have lab testing for those products. Not always. We do have it. I'm not saying they're not great products. We do have a lot of products. Some of them might be great, but unfortunately, unlike what happens in US, is they have this ICC testing reports that you would find. Or IMPO testing report. So there needs to be a testing report for all the such products. In my opinion, in my humble opinion, there should be some testing report that should be coming out. And also, there's fiber wraps cannot. Yes, I agree with you. The fiber wrap cannot be as effective if there's a bond. The bond is not effective, or they are not anchors that. Sometimes you do need anchors actually to connect the fiber wrap to your existing concrete, but the bond really it does matter. I would not pass a blanket statement of how these have behaved in the past in Pakistan, since I'm not truly aware of it.
Okay, Muhammad Awais Qadri is asking, could you please provide resources for practicing the computational analysis of existing buildings?
Okay, if I understand this question right, you can use the same softwares that we use for the new buildings. I mean, ETABS is good enough, but of course, you will not find the default load combinations there. You would have to make your own custom load combinations, but the modeling is the same. You can get the forces out of your ETABS model or any finite element tool, and then you can do hand calc spreadsheets to check for the designs. But yes, I'm not aware of if ETABS can actually check the members for the ASC 41 criteria.
Yeah, now we have a question from Muhammad Azim again. He's asking, is there any research showing how much is the difference in the cost of retrofit in immediate occupancy, life safety, collapse prevention of a frame building. It is useful for client to decide which retrofit performance scheme to select. It is useful for client to decide which retrofit performance scheme to select. Yeah.
Right. So I think I could be on. This might not be incomplete, but I don't think there can be a raw number associated with all types of construction, right? So it would really vary from one building to another building, and there cannot be. For example, you can say it really depends upon the state of your existing structure, how well your existing structure is, and how much more work you need to do. And it would vary from building type to building type between those performance levels. I don't think a raw number can be given for a blanket number can be given from all types of buildings.
Thank you. Now I have really time for only two more questions. So this is the second last question. It is with the clandestine procedure. This question is from Ridwan Mirza. With the
Okay.
clandestine procedure of code writing practice in Pakistan, do you feel that we would not be having rational decision making without an inclusive and transparent code development process?
I agree that the case of existing building is even more sensitive than the new buildings. And the reason for this is because in case of new buildings, you have less to deal with. But in case of existing building, you have a lot of different kind of construction that simply right off the eye, you can see it's not code compliant. So if someone just goes and says that all the brick infill frames are non-compliant, they need to be retrofit. I mean, it can stay in the paper, but it could never ever happen in Pakistan, right? So that's why even in India, although they have very well documentation of their codes, they are not saying that you should not be using so and so, because we need to have an understanding on our limitations and our solutions. I agree to this part that our solutions need to be as per the limitations and requirements of our country, and especially that it varies across the region. And also that's why I would add that in United States, IBC is like the principal governing document over, right? But they still have building codes that are specific to the provinces, and even so sometimes specific to the county level. So there's a LA County building code, there's a California building code, and then there is an IBC as well. So what the intention is that you have different requirements even in a specific region. So it would be very dangerous to say that we have one solution going from Karachi up till the north of Pakistan. There has to be the solutions have to be different to take into consideration different limitations that we have.
Thanks, Rehan. This is going to be the last question now. It is from Muhammad Owais Raza Qadri and is asking, does PSCE 41 or IEBC include specific design criteria for retrofitting schemes?
Yes, IEBC. So like I said, the performance metrics should come, if you're following IEBC, the performance metrics needs to come, if I'm understanding this question right. I hope I'm doing. Needs to come from IEBC, that those were the performance metrics that I was showing. And then ASC 41 will give you the analysis tools, like how you would classify the members and stuff like that. But so yes, so IEBC would give you the performance metrics. It will tell you how to deal with different kind of alterations and additions. And ASC 41 would walk you through the analysis approach. So they go hand in hand in dealing with retrofit schemes. So it's an evaluation and retrofit documents. They cover both of them.
Thank you, Rehan, very much. With this, we come to the closing of the question answer session. Now, I again clarify for our viewers on Facebook and here also that this lecture will be uploaded on our website, I think in a day or so. Then you will be able to, you can read the lecture on the website, or if you want, you can download it also as per your convenience. And there are other lectures also, I think around 60 lectures we have uploaded. So any of the lecture you can read on our website. Some you can download and some you cannot. So this was the announcement. Now, before I go for the conclusion of this session, I would like my co-host Rizwan Mirza, if he wants to say anything, he's free to do so. Rizwan, if you want to say anything, please go ahead.
It was a wonderful lecture. What more can I say?
Thank you, sir.
But it's a slippery slope in Pakistan. I think if I were to follow IEBC, I would end up in prison because there'll be nobody defending me why I adopted a certain risk level, especially if it is a government building. Otherwise, I know this is the state of the art. Thank you.
Thank you, Ridwan, for your comments. And I would also like to thank our overseas participants, Joven Manuvri from Tanzania and Mr. Zhang Jin Liang from China. They took out their precious time from their busy schedule and they attended this lecture. And I hope they have enjoyed the lecture and we would like to see them again and again in our lectures. Now, the announcements. The next lecture will be on 20th January 2024, same time, 2 p.m. Pakistan Standard Time. Our speaker would be Engineer Suhail Kibriya, and the topic is climate change and geohazards. For the collection of the certificates, you can start collecting your certificates from 21st December, which is Thursday onwards, from our office, which is 14A1 Block P, Model Town, Extension, Lahore. And the person before coming, if you want to call to check whether your certificate is ready or not, you can call Ahmad Akram. His phone number is 0347 462 5111. Again, the contact person is Ahmad Akram and his telephone is 0347 462 5111. Rizwan, sorry, Rehan, your
Yes, sir.
sheet would be ready, inshallah, and
Sure.
it will be
Thank you.
delivered to the address that you have given to my coordinator, Sadia Naveed. It will be dispatched to you by courier mail. That you will go, your
Thank you.
certificate and your sheet that will
Thank you,
be
sir.
dispatched, I think, within the coming week. So
Thank you,
with
sir.
this, we come to the end of this session. I thank all the participants here on Zoom and on the Facebook who have attended. And thank you very much for supporting Pakistan Society of Civil Engineers. I would invite the young engineers to come forward and join the society as the committee members and give your input there. We really require young engineers to join us and start working for the society. And I don't think I have any other announcement. So I hope, gentlemen, all of you had a wonderful this year, 2023. I hope you had good success in this year. I wish you, we will be meeting next year. So in advance, I wish you best of the new year. And I hope that the new year will bring more happiness for all of you. Thank you very much, and Allah bless you all. Goodbye.